naked, I'm numb, I'm stupid, I'm staying. And if Cupid's got...
Hi guys, my name is Nako Nakatsuka. I'm a 4th year chemistry PhD student at UCLA, and today I'll be helping you guys out by going over some general chemistry concepts. And good luck with the course. Now moving on to part B of the historical perspectives. Now in 1769, Carl Wilhelm Scheele discovers tartaric acid isomers. So tartaric acid came from tartar, which is the potassium salt of tartaric acid that's deposited on barrels during fermentation of grape juice. So basically it's like wine precipitate. And so they actually found a total of 3 tartaric acid isomers. The first being the tartaric acid with the structure like so, and this was the wine precipitate. And they also found a racemic acid, and the term racemic actually comes from the Latin term racemus, which means bunch of grapes. So this actually came from the whole tartaric acid debacle. And the final one that they found was mesotartaric acid. So since they're all isomers, it means they have the same molecular formula, but they have different arrangements. And they actually found that tartaric acid was optically active, but both of these guys were inactive. And so when they put plain polarized light through a tube containing a solution of tartaric acid, when the light came out, it was rotated in a clockwise direction. And so they found that tartaric acid is dextrorotatory. So we're still on tartaric acid isomers, but now in 1847 came Louis Pasteur. And what he did was he actually separated the racemic acid. So remember, we had the tartaric acid isomers, and we also had the racemic mixture in addition to the meso compound. And he actually separated the racemic acid, the ammonium sodium salt, into plus and minus isomers. And so the plus and minus tartaric acids are actually mirror images of one another. And what was really interesting was that they're equal but opposite optical activity. So if you remember the diagram before, you started out with an arrow that's pointing straight up and straight down. In the case of the plus tartaric acid, it moved it in the clockwise direction by plus 12.7 degrees. But in the case of minus tartaric acid, it moved it in the anti-clockwise direction, so the opposite side, but by the same degree, minus 12.7 degrees. So this was really interesting because he had this racemic acid salt and he was able to separate them into the plus and minus tartaric acid. So in conclusion, the racemic acid is a 1-to-1 mixture of 2 optically active substances. The reason why they could tell that they were in a 1-to-1 ratio was because the degree by which they rotated light was the same. And so this is actually a definition that you can use from now on of a racemic mixture. It's when you have a 1-to-1 mix of 2 optically active substances. And so Pasteur found that the 2 tartaric acid isomers also had different biological properties. And so again, that's really interesting because you start out with the same exact racemic acid salt, you separate them, and just by the fact that they rotate light in the opposite direction, they had very different biological activity. So this is going to be a whole thing that I talk about later on, so keep this in mind as we talk about the rest of the history. So now moving on to part C, we talk about tetrahedral carbon. So in 1874, Joseph A. Lebel and Jacobus van 't Hoff, which you might recognize his name for the van 't Hoff factor, they proposed that carbon with 4 attachments has a tetrahedral structure, which was a really huge thing to discover, and also a molecule having a tetrahedral carbon with 4 different atoms attached exist as a pair of isomers. So that's something that I mentioned before, right? When you have stereoisomers, you have 4 different atoms attached to the central atom. If you have 2 of the same one, they're most likely going to be identical. And so right now I'm going to introduce to you another important term, which is stereocenter. And a carbon atom bearing 4 different atoms or group of atoms has a stereocenter, which is often indicated with this star. And this star is very important because it tells you whether something is going to be chiral or not. But I'll tell you more about that in a little bit. So using our understanding from before, let's look at the stereoisomers of 2-chlorobutane. Let's think back to the flowchart and figure out what kind of isomerism we're seeing. Well, first off, it's not constitutional. And the reason for that being that it has the same atom connectivity. If I want to draw this out, it would actually look like this. And then hydrogens on all the carbons. Like so. So it's not constitutional since they both actually have this configuration. And they are not conformational because they can't be made superimposable by mere bond rotation. They're also not identical because they're not superimposable. Thus, we must have, since they are not any of these, configurational isomers. Configurational. And so these are isomers that differ by the positions of atoms in space that I mentioned before when we were talking about stereoisomers. And they're not constitutional or conformational. And so in this case, let's look at the 2-chlorobutane. They're actually mirror images of one another, but they're non-superimposable. And thus, they're called enantiomers. So this is a very important new term. So think of it as your 2 hands, right? If you have your 2 hands, they kind of look like mirror images of one another. But if you wanted to put your right hand on top of your left hand, it doesn't work, right? Because your thumb would be on top of your pinky, and the same for the other side. And so it just doesn't work. And so that's exactly what enantiomers are. Stereoisomers that are non-superposable mirror images of one another. And so now we're going to introduce the term chiral, which is any molecule that is non-superposable with its mirror image. And so, for example, A and B are chiral. And this center right here, also known as a stereocenter, is also often called a chiral center. And so you can call it either one of those. Achiral, on the other hand, is any molecule that is not chiral. So if it doesn't have a chiral center or a stereocenter, then it's going to be an achiral molecule. Again, just to remind you guys, a racemic mixture is a 1-to-1 or equimolar mixture of 2 enantiomers, just like we mentioned before. And so that concludes our history part, and now let's move on to naming the different stereoisomers.